In this video, I'm going to solve this question on intermolecular forces. Okay, so saying a biochemical engineer isolates a bacterial gene fragment and dissolve a you have a 10.0 milligram sample of the material in enough water to make 30.0 milliliter of the solution. Okay, then the osmotic pressure of the solution is given here to be 0.340 torr. Okay, at 25 degrees Celsius. Okay, so that's the standard temperature at which this mixer was done. Okay, then you have a question here saying what is the molar mass of the gene fragment. Okay, so you have to determine the molar mass of this gene fragment. Then part B, we are going to so they're saying if the solution density is that one, we've been given the density of the solution. Now, how large is the freezing point depression for the solution? Having been given the crystoscopic constant there of water to be 1.860 degrees Celsius per molarity. Okay, so that's what you have in there. Okay, so let's start with the first part, which is asking us to determine the molar mass of this gene fragment. Okay, so from what we know, okay, from more concept knowledge, we know that the molar mass, okay, is given by, so you get your mass, then you divide it with the number of moles. Okay, so that's a formula for molar mass. Okay, so do we have mass here? So let's organize our data. So our main target is to get the number of moles and the mass. Then we can come up with the molar mass of this gene fragment. Okay, so let's collect data. What are we having? Okay, so do we have mass? Yes, we've been given the mass of this gene fragment. Okay, so I'm just collecting data here. So the mass has been given to be 10.0 milligrams. Okay, so that's a mass which was given 10.0 milligram. Okay, now you notice that the units for molar mass is usually in grams per mole. Okay, now here we've been given the molar mass, the mass to be in milligrams. Okay, so that simply tells you that you need to change these units for this mass. Okay, so you need to take them um to grams. Okay, so I will introduce the conversion factor there. So I'll simply convert this milligram to grams by multiplying it with a conversion factor. Okay, what is my conversion factor? I know 1 gram. Okay, so 1 gram is giving me how many milligrams? 1000 milligrams. Okay, so that's what I'm having there, 1000 milligrams. Okay, so that my milligrams and my milligrams there will cancel. I will remain with the grams as unit. Okay, so when you divide there, so you are simply dividing 100 by 1000. You are going to get 0.01. Okay, so 0.01 grams there. Okay, when you divide there. Okay, so that's what you have in there. Okay, so that's the first step. Okay, so you have 10 divided by 1000, which is going to give you 0.01 grams as your mass. This is the mass you're going to use. You have your mass. Okay, so we have our mass here. We are remaining with the number of moles. Okay, so how are we going to get this number of moles? Okay, so we go back to our more concept. Okay, so we know that molarity, which is concentration, is given by number of moles times volume or divided by volume. Okay. So from here, we can make our number of moles subject to the formula. Okay. So we can say my number of moles are going to be given by concentration or molarity. Okay. Times volume there. Okay, that's a formula. Okay, so with this, I should be able to calculate the number of moles there, which we are going to use there. Okay, so what we need is the concentration and the volume. Okay, so let's go back to the question. What have we been given? Okay, so we've been given the volume. you can see there they are saying they are to make to make 30 milliliter, which is the volume. Okay, so we have the volume there. Okay, so the volume has been given. Okay, so okay, so let me wrap this so that I, 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 I create some space. Okay, so we found the mass. So there, the mass, we can replace it. So I can say it is equal to the mass, we found it to be 0.01 gram. Okay, so that's our mass. So we are looking for the number of moles. Okay, so now here we are saying we have the volume. Okay, so the volume has been given to be in 30 mils. Okay, or milliliter there. Okay, like that. Okay, now you notice that when you're doing molarity, okay, so when you're doing molarity, you notice that the SI unit for molarity, it's in mole per deciliter, per cubic decimeter, sorry. Okay, so now you notice that cubic decimeter is the same as, so when you have 1 cubic decimeter, is equal to 1 liter. Okay, so you need your volume. This simply tells that you need your volume in what? In liters. Okay, so I'm going to convert this 30 milliliter to liters. Okay, by introducing the conversion factor as well. So I'm going to multiply with the conversion factor. The conversion factor tells me that 1 liter. Okay, so I want my liter to remain. I'll put them on top there so that my mils or my milliliter cancels. Okay, so I say 1 liter is giving me 1000 milliliter. Okay, milliliter there. Okay, I have milliliter there. So that this milliliter and this milliliter will cancel. Then I will remain with liters there. Okay, so then my volume, when I divide 30 by 1000, I'm going to get 0.03 liters as my volume. Okay, so I have my volume. What I need is molarity. Okay, so here we are simply trying to calculate the number of moles. So we have our volume, so we need molarity. Okay, so now from what we've been given here, how can we get molarity? Okay, so let's go back to our question. The question has given us the atmospheric pressure. Okay, so you can see there the atmospheric pressure of the solution is 0.34 torr. Okay, so we have the atmospheric pressure there donated by liter pi. Okay, so now you know that atmospheric pressure donated by pi, okay, is given by molarity. The molarity we are looking for, okay, times the rate constant. Now the rate constant here we are going to use is that one having liters atmosphere. Okay, so liters atmosphere per more Kelvin. It's the one we are going to use here. We are not going to use the 8.3 is 314 joules per more Kelvin. No, we are going to use the one having liters atmosphere per more Kelvin. Okay, so that's the rate constant we are using here. Okay, then apart from rate constant, we are also going to multiply with the temperature. This temperature should be in Kelvin. Okay, so meaning since we've been given the atmospheric pressure, okay, so we have our atmospheric pressure there. Then we've been given the temperature and we know the rate constant, okay? So we can make our molarity subject to the formula there, okay? So our molarity is going to be equal to, okay? So I've made molarity subject to the formula. So it's going to be atmospheric pressure divided by R, which is the rate constant, times the temperature in Kelvin. Okay. So now this will be equal to, let's put our values there. So let me go back to the pi, the atmospheric pressure. Okay. So you notice that this pi has been given in torr. Okay. So now you notice that the rate constant you have in there, the units, I've said the one you use is in liters atmosphere per more Kelvin. Okay, so now liters atmosphere. Okay, so meaning you need to change this pressure. Okay, so the osmotic pressure, you need to change it from to atmospheres. Okay, we are going to do the same thing when we introduce the conversion factors. Okay, so I'll change it from here. So we've been given 0.34 to. Okay, so now I'll change these units, the to atmospheres. Okay, so by multiplying with the conversion factor, which is telling me that 1 atmosphere. Okay, so 1 atmosphere is giving me 706 706 tau. Okay, so that my tau and the tau there will cancel. Okay, so that I remain with the atmospheres as the units for my pressure there. Okay, then I'll divide with my rate constant. Okay, so now I've said you use this rate constant, which is a 0.0820 okay, liters atmosphere per more Kelvin. Okay, so that's the rate constant you are going to use. Okay, then I multiply it with the temperature. Now again, let me go back to the question. The temperature being given is in degrees Celsius. Okay, but here I have my rate constant having Kelvin as unit, and I want somehow I want my Kelvin and Kelvin to cancel. Okay, so that tells me that I'll need to change my temperature to what? Kelvin. Okay, so I'm having 25 degrees Celsius. So for me to change it to Kelvin, I'll simply add 273. So 273.15. Then this temperature will be in Kelvin. So you simply add 273.15 to it, then you would have changed to Kelvin. Okay, so let's do our calculations there. Okay, so there on top, if we calculate there, we get 0.34. We divide it with 760. Okay, so we are going to get 4.47 times 10 to the power -4 atmospheres. Okay, so remember we converted those to the to atmospheres, so we have in atmospheres here. Okay, so we have atmospheres here. Okay, then we divide with, okay, so here when you add 25 to say 25 to 273.15, you're simply going to get 298.15. Okay, so there you can put 298.15 Kelvin. Okay, so I've converted my temperature to Kelvin so that my Kelvin and Kelvin there will go. Okay, then here again I'm having atmospheres. I'm also having atmospheres there. Okay, so my atmosphere and atmosphere will go. Then I will remain with the more per liter there. Okay, so there, so here I'll simply multiply my 0.08206 with 298.50. So there I'll multiply those two. Okay, then okay, so I'll multiply 0.0 okay 8206 with 298.15. Okay, Then my units are going to be, okay, so let me just do this. So my units are now going to be more per um, per per liter there, okay, or per cubic centimeter, okay, which are the units for my molarity, okay. Okay, so there, the atmosphere, sorry, we cancelled out the atmosphere there. So we only remain with the units for molarity there. Okay, then this will be equal to, so I'll get the final answer. So there, I'm going to get my molarity to be 1.83 times 10 to the power -5 more per liter, okay, as my molarity, okay. So remember, here we are just trying to get our molarity so that it helps us to get our number of moles, okay. So we'll go back to our number of moles here. So we have the molarity and we have the volume, okay. So we can now come up with the number of moles there, okay. So number of moles will be equal to, so we get our volume, which is 0.03 liters, okay. Then I multiply it with my molarity there, which is 1.83 times 10 to the power -5, okay. So 1.83 times 10 to the power -5 more per liter, okay. So that my liter and my liter will go there. I will remain with moles, okay. So there, when I multiply, okay, so when I multiply those two, I'm going to get my number of moles to be 5.49 times 10 to the power -7 more. Okay, so those are my number of moles. Okay, so I have my number of moles, I have my mass, so I can calculate the molar mass, which solve part A of this question. Okay, so I can now calculate my molar mass. So I have my mass, which was 0.01 grams, and this number of moles we've calculated here. Okay, so I will simply divide there. Okay, so I get my 0.01 gram, divide it with the my my number of moles, okay, which are, okay, so which are 5 point, okay, so 5 point, okay, so 5.49, 5.49 times 10 to the power -7, okay, more, okay, so there I divide, so my units will be in grams per mole, okay, so when I divide there, I'm going to get 18215 gram per mole as my molarity there, okay. So we are done with our part A, okay. So just a summary, what you need for molarity, you know that the formula is molarity, for my molar mass, sorry, you know that my formula for molar mass is going to be mass divided by number of moles, okay. So our mass we've been given in the question, but you change it to grams, okay, because the units for molar mass going to be grams per mole, okay. So you change them to grams, okay. Then what you need is number of moles. Now, how are you going to get number of moles having been given the atmospheric pressure and the volume, okay? So you know that my volume, okay, so you know that my volume, I can use it to come up with the number of moles, okay? So how do we come up with the number of moles? We know that more number of moles is equal to molarity times volume, okay? So we have volume there. What we need is molarity, okay? So we'll go back to the formula for osmotic pressure, which is MRT. The M is the molarity. We make it the subject of the formula. We get our molarity plus our volume there. So we multiply these two. Okay, so molarity times volume, we get our number of moles. Then we should be able to come up with the molar mass of this gene fragment. Okay, then part B is asking us um to what to know how large are the freezing point depression. Okay, so we have to determine the freezing point depression for this solution after mixing. Okay, so what is freezing point depletion? Okay, so this is one of the cognitive properties you are going to have. Okay, so it happens when the solute is dissolved in a solvent. Okay, then when you dissolve your solute in a solvent, you cause the solvent to reduce in the what? In the freezing point. Okay, so the freezing point of that solvent will reduce. Okay, then that is what we call the freezing point depression. Okay, so how do we determine it? Okay, so freezing point depression donated by change in TF. So we can say change in uh, TF is equal to, so this is the freezing point at depression. So will be given by the KF. So I said the KF is the one we've been given in the question, which is the crystoscopic constant. Okay, so then we multiply it with the molarity. Okay, so the molarity we are talking about here is different from the other molarity we are doing. Okay, so here we are talking about molarity. Okay, so the molarity we are doing in the first part is this one. Okay, so molarity. So there's an R there, but with this one, you're having an I. Okay, so the one with an R, you notice that the units are going to be in more grams per mole. Okay, so grams per mole. Those are going to be the units for this molarity. Okay, but for this one, for the molarity with with so molarity with I, okay, so you're going to have your units to be in mole per kg. Okay, so that's what you're having. So now here, the molarity we are talking about, it's this one, which is having units for mole per Kelvin. Okay, so you have to ask, how do we determine that molarity? Okay, so we determine molarity, so apply a formula. So molarity will be equal to number of moles. Okay, so the number of moles we've already found from the previous question or previous part. Then we divide it with the mass, and the mass we are talking about here is the mass for the solvent. Okay, so divide it with the mass of the solvent. Okay, mass of the solvent. Okay, so now take note, we need our units to be in moles. So molarity has to be in mole. Then this mass has to be in kgs. Okay, so that we have our molarity in mole per kg, like that. Okay, okay, yeah. So let's try determine the molarity of this. Okay, so we have the mass, so we have the number of moles from part A. Now what we need to come up with is the mass. Okay, the mass of this the solvent. Okay, so now from what we've been given in the question, we've been given the density of the solution. Okay, so we've been given the density of the solution, and also we have the volume of the solution. Okay, so we have this volume of the solution and the density of the solution. So that tells us that we are able to calculate the mass of this solution. Okay, so you know that mass is given by density multiplied by volume. Okay, so the density, the one we've been given in the question, so which is 0.997 grams per milliliter. Okay, so we have our 0.997 grams per milliliter. Then you multiply it with the volume, which was PAT. So no need of changing this volume to liters because our density is having units in milliliter. So even our volume here should have units in milliliter, so that the milliliter and milliliter there will cancel. Then you have your mass in grams. Okay, so there the mass you have is 29.97 grams. Okay, as your mass. Okay, so this is the mass of the solution. So here we can say mass of the solution. Okay, so we've determined the mass of the solution. Now we don't need the mass of the solution. The formula here, I said we need the mass of the solvent. Okay, so how do we get the mass of this solvent? Okay, so we are going to get the mass of the solvent. Remember from the question, we've also been given the mass of the solute. Okay, so here, if you read in the question, it was dissolved and dissolves air. So this is the solute which was dissolved, which is 10.0 milligrams. Okay, then we can take it to grams. We can convert that milligram to grams, which we've already done in the first part, which is 0.01 gram. Okay, so here we have the mass of the solute and the mass of the solution. So we can subtract those two to get the mass of the solvent. Okay, so mass of the solvent is equal to mass of the solution. So the entire solution, the entire mixture, minus the mass of your what? Your solute, in which the solvent was dissolved. Okay. So this solvent managed to dissolve this mass of a solute, which was 0.1. Okay. So the entire mass of the solution is the one we've calculated, which is 29.97 grams. Okay. Then the mass of the solute, which was dissolved, is 0.01 gram. Okay. Then we subtract there. Okay. So when you subtract there, should be able to get 29.90 grams. Okay. So 29.90 grams there as the mass of our solute. Okay. Now, remember, our units here are in more per kilograms. Okay, so you need to convert these grams to kilograms. Okay, by multiplying it with the conversion factor. We know that 1 kilogram is giving us 1,000 grams. Okay, so we have 1,000 grams. Okay, so that the grams and the grams will cancel there, then we remain with the kilograms. Okay, so this will be equal to, so we knew, well, we divide our 29.90 by 1,000. Okay, so we are going to get 0.2990 there. Okay, kilograms. Okay, so we have our mass in kilograms. Okay, so we have everything need here, so we can calculate our mass there. Okay, so let me just lab on top. Okay, so let me just create some space here. Okay. Okay, so here we are going to have our our molarity of the solvent, which is going to be our molarity is going to be the number of moles which we've determined. Okay, so the number of moles were 5.49 times 10 to the power -7 moles. Okay, moles. Then we divide with the mass of the solvent, which we've calculated here to be 0.0, okay, so 0.02990 kg, okay. So our molarity now is going to be, so when you divide there, you're going to get 1.8, okay, so there's a point there, 1.84 times 10 to the power -5. Okay, so -5 more per Kelvin. Okay, which we need the here. So I said this molarity is this one with an L. The one said the unit has to be in moles per kg. Okay, so we've gotten our molarity there. Okay, then we have this formula here, so we can now calculate our what? Our freezing uh okay. So let me just there. Okay. So we have our crystal field constant there, then we can calculate the freezing point depression there. Okay, so we have um, our crystal field constant. Okay, our crystoscopic constant there is this one here, which is 1.86 degrees Celsius per molarity. Okay, so the molarity there, that small m simply stand for this molarity which we've calculated here, which is the units are in mole per kg. Okay, so here it's 1.8, okay, 4, okay, so sorry, 1.86 degrees Celsius per molarity. Then we multiply it with the molarity we've calculated, which is 1.84 times 10 to the power -5. So this is the same as the molarity, small letter m, okay? So that this and this will cancel, okay? Then we remain with our degree Celsius there, okay? Then when we multiply those two, we are simply going to get our freezing point of depression to be 3.42 times 10 to the power -5 degrees Celsius. Okay, so this is uh, how large the freezing point of depression of this solution, okay, which is 3.42 uh, 42 times 10 to the power -5 degrees Celsius. Okay.